All right, in this lesson, we are going to look at exponential growth and decay application problems from real-world situations. We're going to start with a warm-up of what we learned last class. It's how to look at a table and be able to identify our equation and some key features of this graph. And so first of all, just looking at the y values, as our x's increase by 1, we see that our y values are growing. Okay, so this would be an example of growth. And we can see our y-intercept is 0, 5. You're always looking for where x is 0. And so our y-intercept is 5. And then to find our common ratio, we can tell that these values are being multiplied by 2, but it's not always that obvious. And so we also have the other strategy of calling our y-intercept y1, and then the very next y value, y2. And so to find your common ratio, which is b, we do y2 divided by y1. So in this case, it's 10 divided by 5, which would give us a 2. Okay, and so now that we know our a, which is 5, and our b, which is 2, we can write our equation. Y equals 5 times 2 to the x, a times b to the x. Okay, from there we know our domain is always all real numbers. And then our range in this case, it's all the positives. All our y values are positive, and so y is greater than 0. And then the asymptote for a times b to the x is always going to be y equals 0. Okay, so in these next examples, we're going to look at where exponential growth and decay come up in real-world situations. And usually you are growing and decaying by a percentage. And so our b value is going to be represented by 1 plus r and 1 minus r. This a value is still our y-intercept, but for real-world values or situations, we're going to call that the starting value. The starting value for when the time is 0. Okay, and so t, our exponent, instead of x, we're using t because that represents the time. And then this r value that we're adding and subtracting from 1, that is our growth / decay factor. And it's important that you convert it to a decimal. It's going to be a percentage, and you have to convert it to a decimal. Okay, and so for the growth model, you're going to start with your starting value, and then you're going to add that percentage to 1. And then for decay, you are going to subtract that percentage from 1. Always from 1, because that 1 kind of represents the 100%. And so you're keeping 100%, but you're also adding a percentage to it. Okay, in the decay model, you're starting at 100%, but you're losing a percentage. And so it's always important that you have that 1 there. You don't want just like a negative r. You don't want just the r value itself, and that's a common mistake. Okay, so looking at some examples, I can see in number 1 that my starting value is 2, and then I can see my r value is 0.45. Okay, so in decimal form, that is 0.45. In percentage form, you would move your decimal, and so this would say it is growing by 45%. We have a plus, so it is growing by 45%. Okay, in this next example, I just see a 0.75 there, and so I see my starting value is 100. And then if you compare this 0.75 to 1, that's 1 minus 0.25. Think if you have 75 cents, that means you spent a quarter of your dollar. And so 0.75 is 1 minus, so we are losing 25%. This would be decay. 1, we recognize that right off the bat because 0.75 is smaller than 1. And so we are actually losing 25%. So this is decay by 25%. My R value is 0.25. Okay. This next one, it's a little bit easier to see when it's bigger than 1 because 1.05 is the same as 1 plus 0.05. And so I can see my starting value is 175. And then I can see my R value is 0.05. That's what we are adding to 1. So since we are bigger than 1, we are adding to 1, we are growing. And we are actually growing by 5%. Think of moving your decimal to convert it back to a percent, because right now it's in decimal form. Okay, so that's how you interpret the equation. Now we're going to go in reverse. We're going to give you the situation and you write the equation. So this number 4 says we are starting with 250 rabbits in a population research study. The population is increasing at a rate of 7%. Okay, and so 7% in its decimal form, we'd have to move the decimal back 2 places. And so 0.07. So here my R value is 0.07. My starting value is 250 rabbits. And because it says the word increasing, that means it is growth. Okay, and so we are starting with 250, that's our A value. And then we are growing, so 1 plus that 0.07 raised to the time, t power. Okay, and so in its simplified form, we would go ahead and add the 1.07 and have 1.07 as our B value. And so it's very important that you have that 1 plus. If you don't have that 1 plus, you're just multiplying by 0.07. That's not going to grow. That's going to decay, and it's going to decay very fast. That's saying you're only keeping 7% of your rabbits, and we are gaining 7%. So add it to the 100%, the 1. Okay, this next example says a new car is purchased for $35,000. And it depreciates, okay? Depreciate is the opposite of appreciate. And so anytime you see that word D, think decay. And so this is depreciating, decreasing, decaying by 20%. Okay, so 20, move your decimal, would be 0.2 as a decimal. And then our starting value is 35,000. If you want, you can just treat it as 35, or you can add the 3 zeros at the end for 35,000. And so my equation would then have 35,000 as my starting value. And then because we're decaying, it would be 1 minus. We're losing 20%. We are not gaining 20%. That would be a very different situation. Okay, so we're losing 20%. And so when I simplify this, 1 minus 0.2 would be 0.8 in that parenthesis. Okay, and so if we're losing 20%, that means we're keeping 80%, which is still going to decay. We're not keeping more than 100%. We're keeping only 80%. So that is going to decay. And so that's how you can read this equation, just like we were doing above. And so read it as you're keeping 80%. You would read this equation as you're losing 20%. It's the same thing, just a different way to interpret what you're looking at. Okay, a good distractor for this question would to have that 0.2 in the parenthesis as your factor, but that's not correct. That would say you're keeping 20% and we're actually keeping 80%. So just notice the difference between those two problems. All right, so now we're going to start from scratch and start answering some questions. We may need our calculator for this, especially since the numbers are large and we're dealing with like 18%, and so we will use the calculator. And so it says Quinn purchased a new luxury car for $95,725. The rate of depreciation, there's our decay, each year is approximately 18%. Does this scenario represent growth or decay? Justify your reasoning. So we can say decay because the word depreciation. Depreciation means decay. Okay, identify the A. the R and write the equation. So A is the initial value, which they told us was 95,725. And then R, they said it was depreciating by 18%. And so 18 in its decimal form would be 0.18. Okay, and so that means our equation is going to start with the 95,725, and then we are losing 18%. We are not keeping 18%. So we're starting at 1 and we're losing 0.18. So make sure you have a 1 minus there. You can simplify that if you wanted to, or you can leave it as just 1 minus 0.18. Okay, and so to figure out the value each year, we can open Desmos, or you can use your graphing calculator. I am a big fan of Desmos, so I'm going to go ahead and open that. And so let's type in our equation. Y equals 95725, parenthesis 1 minus 0.18, raised, you do a to the b, to the x. Okay, you can use x instead of t, or you can type t. And so here I don't see my graph because that 95,000 is very, very large. But honestly, it's better to use the table anyway. So what you're going to do is press the gear and then click the table, and then you're going to see all the values you need. Okay, and so at time 0, we see it's the initial value, the 95725. We could have answered that without Desmos. And then at 5, 10, 15, we can see our future values. Okay, so at 5, we are at 35,489. And then since this is money, we're going to keep 2 decimal places. So we would just say 0.07 cents. For the 10, we have $13,157.21. And then at 15 years, we're at $4,877.90. Okay, so you see it depreciates very, very quickly after 15 years, which is a long time to keep a car. It's only worth less than $5,000. So it says, how many years will the car be worth less? After how many years will the car be worth less than $10,000? Okay, and so looking at our table, we can see it's somewhere between 10 and 15. So I'm going to type 11, not yet, type in 12. That's the first time it's less than 10 years, or less than 10,000. And so after 12 years. Okay, it's actually somewhere between 11 and 12. So if you even wanted to type 11.5, you could get a little more accurate. So even at 11.5, we're there. And so you could say 11 and a half years. So it just depends on how many decimals they want you to keep. We can try 4. We can try 3. And so you can get as close as you need to just by typing in some decimals. Okay. This next example says in 2000, year 2000, gold costs $1,500 per ounce. The price of gold has been increasing by 15% per year. Okay, so I'm kind of picking out some important information. Does this scenario represent exponential growth or decay? Justify your reasoning. Okay, so we know this is growth because it's increasing. The value is increasing. Okay, identify the initial value. They said $1,500. And then increasing by 15%. Okay, so 15 in its decimal form would be 0.15. And so our equation, be careful, this is where the mistake happens. We're starting with 1,500. I wrote 15,000. Get rid of one of those zeros. 1,500. And then we are gaining. So start with 1 and add your 0.15. And then don't forget your variable. If you want to use t, you can use t. If you want to use x, you can use x. So that 1 plus 0.15. If you just put 0.15, that is not going to grow. That is going to decay very quickly. Okay, and so this one's easy to simplify. So if you want to write it as 1.15 inside those parentheses, it takes just as much effort to type the plus as it does the decimal, so either way. Okay, and so going back to Desmos, we are typing in our new equation, which is y equals 1500. And then we have 1.15 raised to the x. Get your table, and we see 0, 1, 2, and then at year 2000, t is 0. Okay, that was our starting, was 0. So by 2005, t is 5. By 2015, that's been 15 years. By 2020, that's been 20 years since our initial value, and then 2050 would be 50 years. Okay, and so at time 0, we're still at the original 1500. By year 5, we're at 3017, and then 03 would round up to an 04 because of the 5. And then at 15, we see we're at 12,205 and 59 cents. And then at the 20, we're at 24,549 and 81 cents. And then at the 50, that's a lot. That 10 to the 6 is million, and so we can say 1.6 million. That's the power of exponential growth. It grows, and it grows very, very quickly. Okay, and so here are some multiple choice questions that involve these exponential applications. These come from STAR, and so I wanted to make sure you see how they could ask about these equations on the STAR test. All right, so looking at number 1, it says scientists are studying a bacteria sample. The function f of x equals 500 times 1.15 to the x gives the number of bacteria in a sample at the end of x days. Which statement best represents the interpretation of one of the values of this function? Before I even look at what they're saying, I'm going to look and see, well, this 500 is my starting value. And I can see that my b value is 1 plus 0.15. And so that tells me it's growing, because of the plus, by 15%. Okay? And so it says, A says the number of bacteria increases at a rate of 15%. Hey, that's correct. The initial number of bacteria is 15. That is incorrect. It should have been 500. So we're not going to choose B. The initial number of bacteria decreases at a rate of 85%. That is not correct. We would have had a 0.85, or actually we would have like a 0.15, 1 minus 8.85. And then the number of bacteria at the end of 1 day is 500. That's not true. If we plug in 1, we would have multiplied the 500 times 1.15, and we'd have less than 500. Okay, and so the correct answer for this is A. Number 2, a student used h of x equals 8.00 times 1.036 to the x to show how the balance in a savings account will increase over time. What does the 8.00 represent? That is the starting value. So that means he's starting with $8. So we know that's in the starting value spot, the A spot. And so we need to look for something about the starting value. And so D says the starting balance. Okay, it's not the interest, it's not the number of years, it's not the annual interest rate. Okay, Here we're looking at a graph. It says the graph of an exponential function is shown on the grid. Which dashed line is an asymptote? Okay, so remember, an asymptote is the line that we approach but never cross. So it looks like S is the line we are approaching but never crossing. T is too low. And then we know exponential functions don't have vertical asymptotes. It looks like it's kind of approaching this asymptote, but it's actually going to cross it. It's going to keep growing and going to the right forever. The domain is all real numbers, and so this is not an asymptote. And so the correct answer for this one is line S. Okay, and then this last one says, which statement about the graph 8 times 0.25 is true? Okay, so just looking at our choices, the equation of the asymptote is x equals 0. That x should be a red flag to you. It should be y equals 0 because we only have horizontal asymptotes for exponential. Horizontal line. You could graph that in Desmos and see that x equals 0 is vertical. The graph includes the 0.21. We'll check on that in a second. The coordinate of the y-intercept is 0, 8. That's true. That for sure is true. We see our y-intercept is 8. And so we know that's correct. And then it says the coordinate of the x-intercept is 0.250. That is not true. We are never going to reach the 0. That's where the asymptote is. And so the other thing we don't know is whether or not B is true. So if you want to verify, I would have just chosen C because I know for sure that's right, but maybe one or more could be correct. And so you can type it in, 8 times 0.25 raised to the x. And then you can see that we, if I graph or get my table, the 0.21 is not on my graph. It's 2, 0.5. And then we never actually touch the 0 line. So you can zoom all the way in and see that we're never actually going to cross the x-axis. We just get infinitely close, and so there isn't going to be an x-intercept. Our range is specifically y greater than 0, not equal 0. So you won't have that x-intercept.